One,
Testing,
two.
testing.
1, 2, 1, 2.
Yeah, I think so.
All right. I can probably project this.
Okay. Good morning, folks. We can do better than that. Good morning, folks. Good morning. Good, much better. Welcome to this inaugural Kevin L. Hawkins Endowed lecture series focused on the business of science. And I was going to introduce, well, there he is, Mr. Hawkins, if you'll stand up. As many of you know, he's a Morgan alumnus, a local businessman, and a board member of the Morgan Foundation. And it was in that context that we met and had a chat, and and that chat led to this series that we're about to kick off. We are truly honored to have Dr. Eric Cornell as our lead off-hitter in this series. Eric is an employee of the National Institute of Standards and Technology, and also he does his research in something called JILA, which means the Joint Institute on Laboratory Astrophysics. It's a joint institute between the National Institute of Standards and Technology and the University of Colorado in Boulder. And although these days I don't think they're doing a lot of astrophysics these days, doing world-class physics, one of the top physics institutions on the face of the planet, Eric is going to sort of talk about some astrophysics as well. He's going to look back into time and share with us how we collect evidence, fossils of the Big Bang. And as most of you know, before coming to Morgan, I spent 45 years at that institution, the National Institute of Standards and Technology. I worked at every level of the organization during that time, and as I progressed, my attitudes about tech transfer changed. Early on, for me, like all scientists there, we are interested in our science. We want to, for me, I wanted to have 200 publications before I retired. I didn't quite get there, but that was the ambition, and tech transfer was the farthest thing from my mind. But certainly as you progress, you begin to learn that in order to fulfill your mission at an organization, be it a federal research laboratory like NIST or an organization like Morgan, we have to support the nation's economy and its economic growth. And we do this by managing technology transfer. During its history there at NIST, there were a number of, what I call these, there were a number of ideas that were developed, technologies that were developed that we chose not to patent. And again, I put a question mark because I'm not really sure at this point whether that was right or wrong. Certainly at the time, we chose not to. But there are things like algorithm for character recognition, laser tracker, the laser French, the chip scale atomic clock, lots of stuff that we actually developed but did not patent. Someone else did and made a ton of money. The last two things down there in red were discoveries that I made. And had I been a smart businessman, I wouldn't be working now. One was high-performance LC liquid chromatic graphic columns that give me a separation problem, and I can tailor that stationary phase to optimize it for that. A company, YMC, picked that up, made a lot of money. But the first one is one of my first assignments, you would have seen it on the slide, was to be a part of a small team that did a pollution baseline assessment in Alaska prior to the completion of the Trans-Alaska Pipeline. And necessity is the mother of invention. And one of the concepts I developed was solid phase extraction. And anyone who's done any organic analysis, ALC, has heard about that. And it was just simply, instead of bringing buckets of water about, we pushed the water through a resin, concentrated all of the organics, and brought those back to analyze them. Well, Waters commercialized that, made a ton of money on it, and basically, I gave it away. We have examples of tech transfer from our Nobel Prize winning scientists. As I said earlier, or I didn't say perhaps, NIST scientists have won 5 Nobel Prizes in the past 20 years. And we have the second of those here with us. My guess is Eric, Dr. Cornell, probably is one of the youngest physicists ever to win the Nobel Prize, and he can tell us, he can share that with us, whether that's true or not. But there have been lots and lots of spinoffs. But those folks, I'll be honest, didn't come to NIST and spend their career to do tech transfer per se. They came to do cutting-edge, world-class science. But it's the responsibility of the leadership of that organization to make sure that, number one, the organization benefits from that research, but more importantly, that our country benefits, because so much of the technology that is developed in this country is actually commercialized offshore. And that becomes an economic problem, but also in many cases, it becomes a national security problem as well. Here are a few figures of merit for tech transfer. Actually, you can see that the current director is focused, laser focused on tech transfer. He's not as involved with managing the scientific program as perhaps I tried to be, but he is a person from a tech transfer background, and you can see the last 2 years, 2017 and 2018, an uptick on those type activities. I come to Morgan, and I find that Morgan actually has an Office of Technology Transfer and has a tech transfer officer par excellence in Mr. Wayne Swan. Stand up, Wayne, and take a bow. If you look at those merits there, if you look at NIST, and this is the world's foremost metrology measurement standards institute. But in terms of disclosures, you can see 71 patents issued. You can look at those numbers, and that's now. And look at what we have at Morgan. Now, the research budget for Morgan is less than $50 million. The research budget for NIST, it approaches $1 billion. So a big difference. But in terms of intellectual disclosures, Morgan had 21 past year. NIST had, so certainly, and if you go back to 2016 or so, really punching above our weight, and we must continue to. So that brings me to the introduction of our speaker. And let me catch up with my notes. As I said earlier, Dr. Eric Cornell received his Nobel Prize in 2001 for his realization of something called the Bose-Einstein condensate. It was a state of matter that had been predicted by Einstein and Bose back in the 1920s, but no one had ever been able to realize it until he, along with his colleague at JILA, Carl Weinman, actually did so. And about the same time, there was another colleague, Wolfgang Ketterle at MIT, who was doing similar experiments, and they actually got the Nobel. They received the Nobel Prize jointly in 2001. I've asked Eric to say a few words about his research and some of the commercial spin-offs. And hopefully he'll do this. But the main topic of his lecture will be looking for fossils from the Big Bang. Please give a big Morgan welcome to Professor Dr. Eric Cornell.
Thanks very much. I'm going to swap over to the other program. Should be right here. Well, thanks very much. As Dr. May told us, I think of him as Director May. For many years, he was my boss, so I got to be on my best behavior. Still think of him as my boss. I'm planning to talk about eventually something which is the research which I'm doing in these last few years. But I was asked to talk a little bit about the stuff for which I won the Nobel Prize and particularly the applications of that. So that was called Bose-Einstein condensation. And I'll give you just a couple minutes overview of that. I wonder if it could get just ever so slightly darker up here. I don't know. Well, it doesn't matter. This probably works okay. You can see here a thermometer. It's an absolute scale, so we measure temperature in physics and chemistry, geology. We measure it in Kelvin. 300 Kelvin is more or less room temperature. 0 Kelvin, absolute zero, is the lowest possible temperature. And where the Bose-Einstein condensation occurs is so close to absolute zero that you can't even resolve it on this scale. If we were to expand this up a little bit, so deep space, the lowest possible temperatures you can see in the universe out in the space between the stars is like 3 Kelvin. We go a whole lot colder yet from 3 Kelvin. If we compare 3 Kelvin to the height of Mount Everest, then the temperature where this Bose-Einstein condensation happens is at 100 billionths of a degree Kelvin. It's kind of like the comparison between the height of Mount Everest and the thickness of a pencil lead or something like that. So it's tremendously low temperatures. It's super, super cold. And I don't plan to go into that today. As I said, this is just kind of a preface, but we used lasers to get things cold, and that's a little bit counterintuitive because you think of lasers as, I don't know, super hot for cutting out patterns of shoe leather or what have you, but Bill Phillips, who is the first NIST person to win a Nobel Prize, developed techniques for using lasers to cool atoms. My colleague Carl Wyman and I extended it to a different kind of cooling involving magnetic traps with some atoms, the hottest atoms falling out of this sort of magnetic bowl in which we're keeping the atoms. The atoms got very, very cold, and that temperature, this is in nanokelvin, so billionths of a degree of about absolute zero. It got 400 billionths. This is now just sort of a gas of rubidium atoms. It got colder. This sort of shark's fin thing appeared. This was the condensate, which appeared way back in 1995. And sure enough, it was a big deal. As I say, it's not really the topic of today's conversation, but by the way, can people hear me okay? Is this working out there? Okay, yeah. So that was the topic of the Nobel Prize. People have, in the intervening 2.5 decades or whatever it is, there's thousands of people who have worked on it. They've written tens of thousands of paper. I was asked to mention a little bit about some of the technological applications. And I would say these days it seems clear that one of the most important technological applications has to do with this. What is this? This is an array of 5 by 5, so a total of 25 individual atoms. People have gotten so good at detecting single atoms that they can now detect individual atoms. And I want you to think about these atoms as very much related to bits in computers. So 25 individual atoms, think of them as a bit, in this case as like a quantum bit. This is as small as a bit can possibly be. Inside a chip in your telephone, what have you, a bit, a 1 or a 0 is usually made up of a couple transistors and a few additional circuits. It's very, very small inside your telephone, but it's not as small as a single atom. And these bits, like computer bits everywhere, can be 0 or 1, or because they're quantum bits, they can be 0 and 1. And this is sort of the mystery of quantum mechanics. It's again, not where I'm going today to talk about this thing called quantum computing. It's a little bit of a trite thing to say it's a new paradigm. This is the new paradigm of, you hear this people introducing technology all the time. As soon as someone says, this is the new paradigm for, I start to doze away because I figure, okay, this is some serious hype. But quantum computing really is a new paradigm for computing in the future. No one can be sure in the future what a functional quantum computer will look like. There's a vast amount of industrial effort and university effort going into making something like this. This is a reality, this array of 25 bits, turning it into having the ones and zeros talking to each other in such a way as to make gates, input and output devices. Turning the whole thing into a computer is a ways off in the future. No one can be sure what a fully functional, useful quantum computer will eventually look like. But one thing we're almost certainly going to be sure about is that it will have to be very, very cold. Quantum mechanics fears hot temperatures. Quantum mechanics works best at very, very low temperatures. And so that, right now, seems to be the most sort of productive, technologically relevant direction of this very cold gases that Carl Wieman and I invented. This is supposed to look like, this is supposed to be an old-style ice cream churn. You put ice around the outside. Inside, you have strawberry ice cream, and you turn the handle. So I want you to think of the strawberry ice cream, which is my favorite, as quantum computers. And then around the outside, we've got Bose-Einstein condensation. So in fact, many of the concepts for quantum computers basically involve the things being immersed in this super cold gases. Other possible directions, so I should say that in my lab, the people who have come to my lab and done research, which they thought of as being kind of purely scientific research, like Dr. May, they wanted to write papers about it and become university professors. A large fraction of them graduated from my lab and got snapped up by companies to work instead on quantum computing, because it's where the money is. Much more so than in university professoring or in federal employing, I'm sorry to say. Other possible directions for very cold gases, there's a whole sort of field of study called nanotechnology, making devices the size of molecules, and electronic circuits, again, also sort of comparable to the size of molecules. If anything we know about the future of technology is that it lies in the direction of the very, very small. This is supposed to be individual electrons traveling along wires coming towards some sort of, this is supposed to conceptually represent gates. As things get smaller and smaller, instead of thinking about the electrons as particles, we have to think about them sort of as waves. And quantum mechanics is the science of waves. And we know that when waves pass through each other, you get interference patterns, fringes, waves overlap and interfere constructively and destructively. And to understand that, you have to have a very, very deep understanding. If you want to make progress, I would say, in technology at this very small level, you have to have a very deep understanding of quantum mechanics, which is the science of the super, super cold, and the super, super small. So we can think then of, okay, so is Bose-Einstein condensation small? No, these gases are relatively large, but the effect of making things very cold expands the effect of quantum mechanics, so you can actually see and really deeply understand and design these very small things. So in terms of technological relevance for Bose-Einstein condensation, you can think of it as an air conditioning unit for a quantum computer, a teaching lab, but a very high-level teaching lab for generations of scientists, and I should say of engineers, of technology people, for understanding how quantum mechanics works at this very fundamental level. It's the science of the very small, which is the direction of future technology. And then as a more specialized thing, there have been some spin-off companies which take Bose-Einstein condensations and use them as sensors for rotation and accelerators. So acceleration, I should say. I think I am not allowed to know, but apparently there's some effort to put these things inside of submarines and so on for navigation, what have you. That was a little bit of a whirlwind tour through stuff which I did low these many years ago, but I did think it would be, I thought it nice to sort of review that. What I would really like to talk to you more about today is looking for fossils of the Big Bang. And I came up with a title which I thought was a little more churchy. 14 billion years on, what can we learn about original imperfection? Behold, we were shapen in asymmetry. This is my text for today. We were shapen in asymmetry, and in perfection did the universe conceive us. I'm looking for, okay, some people might recognize Psalm 51, but anyway. We're going to go back a few years, 14 billion years before this presentation at Morgan State, which was the moment of the Big Bang. This is my artistic representation of the Big Bang. This was the beginning of the universe. The whole universe was in a hot, dense state, as the creation hymn goes. And after a little while, the universe expanded and particles started to precipitate out. We know that the world and the universe is mostly made up of electrons and protons and neutrons. For every particle in the universe, there's a kind of particle called an antiparticle, an anti-electron, which I've written like this with a bar on top, an antiproton, an antineutron. Immediately after the Big Bang, there was a lot more stuff in the universe than there was today. The universe was full of particles, protons and antiprotons, electrons and anti-electrons, neutrons and anti-electrons. There was about 1 billion times more stuff, particles in the universe back then than there is now. Where did all that stuff go? Well, as the universe got a little bit, the universe expanded, and we know from chemistry class that things expand and they get colder. That's what happens when things expand. These things got a little further apart, they started to cool down, and what happened is something very romantic. The protons found the antiprotons, the electrons found the anti-electrons, the neutrons found the antineutrons. All around the universe, each particle found its true soul mate. Okay, well, married life was passionate but very short. What happens is you get a proton and antiproton, they stick together for a little while, and then they annihilate each other, bang, bang, bang. One after another, all the pairs of particles, the proton and the antiproton, when you meet your anti-partner, you stick together, and then poof, you disappear in a hail of light, basically little particles of light. There was back then a whole lot more stuff and a whole lot less light. Now there's a lot more light in the universe and a whole lot less stuff. If we look around the universe, there was about, for every 1 billion protons, there was like 1 billion antiprotons, there was 1 billion plus 1 protons. There was like 1 billion electrons, there was 1 billion plus 1 electron. 1 billion neutrons, 1 billion plus 1 neutron. So as everything sort of paired up and disappeared, there were a couple particles, just here and there, just a small number of particles, like 1 part in billion of stuff that didn't like disappear. Yeah, almost everything disappeared. So who are these final few particles that no one wanted on that big sort of New Year's Eve 14 billion years ago? Yeah, they're you. I hate to put it that way, but yeah, it explains a lot, doesn't it? Sometimes about it. Yeah, so I want to say it was a good thing, right? This tiny little imperfection, this fact that there weren't exactly the same number of protons as antiprotons, same number, the fact that it wasn't a perfect matchup was an awfully good thing. This is why we're here. So this almost perfect matching up in matter and antimatter was not exactly perfect, and we were born of this original imperfection. So how can we learn more about it? We can't go back in time machines. There's no like scrolls to read about. And we can think about it, how do we learn about dinosaurs? Still can't go back in time machines to look at dinosaurs. And I have 3 possible ways of doing it. One of them is big telescopes. The way science thinks about these things is big telescopes. Light travels very fast, but it doesn't travel infinitely fast. If we look out and see a galaxy 10 million light years away, we're seeing that galaxy the way it looked 10 million years ago. If we look out with the biggest telescopes we possibly can get, as far as we possibly can to the furthest away things we see, which are 13.3 billion light years away, we're looking at that galaxy the way it was when the universe was only 4% as old as it was today. We're looking at sort of baby galaxies from back in the baby days. But we can't look all the way back to that era of the original imperfection when the particles were sticking together, because that's just too far away. The universe was opaque back there, so that won't work. What's another idea? Well, another idea is we could use particle colliders. We can take particles and slam them together at tremendously high energies and sort of simulate where the particles smash together. In that little zone where the particles are smashing together, we can simulate the very hot, very dense environment of the early universe. And the largest scientific instrument that was ever built was the LHC, the Large Hadron Collider in Switzerland and France, where they collide protons together at the highest energies they ever did. And apparently, that huge project has been, for the particle physicists, a little bit of a disappointment. It looks like they haven't quite gotten to the point where they can see explanations for things like this original imperfection. So I want to talk about a third possibility, which is looking for fossils. Here we are, we want to learn about dinosaurs, we look for dinosaur bones. So what I'm looking for is fossils of the original imperfection, this original breakdown of symmetry. There's a lot of symmetry in nature. Here's a beautifully symmetric snowflake. But what I'm talking about when I talk about symmetries are one of these three basic symmetries that you see all around nature. One of them is that electrons act just like electrons, anti-electrons, or pretty much. The other thing is that most particles, if you look at the particles in the mirror, they look exactly the same. When people look at themselves in the mirror, they look pretty much the same. Actually, not so much. I see someone missing his right arm. So it's probably no coincidence that about 15 years ago, I took a great deal of interest in this sort of asymmetry. Also, they look the same if you run the movie backwards. I'm not talking about dropping a glass. If you drop a glass, it shatters into a million pieces. If you were to run that movie backwards, it would look like the pieces would come together and stick to a glass. That would look very different. But when individual particles, electron and a proton, when they bounce off each other, if you were to take a movie of that and run that movie backwards, it would look perfectly the same. You wouldn't be able to tell whether the movie was running forward or backwards. So these are the three symmetries that happen in nature. And there's a key assumption, call it a prejudice or a hope, that fossils don't vanish, that whatever that original imperfection was, that breakdown of symmetry between protons and antiprotons way back when, that there still has to be a residual asymmetry today, that the laws of physics haven't changed, that we ought to be able to find that imperfection in the imperfections of particles we see today. So I'm not going to go through the particle physics arguments. I couldn't, even if I wanted to, because they're very mathematical, and I'm sort of a soldering iron, oscilloscope, hands-on sort of person. And this kind of level of math is beyond me. But what I'm able to understand from that is that various sorts of imperfections tend to balance each other out. So if there was an imperfection between the electrons and the anti-electrons, the protons and the antiprotons, then those should show up in other imperfections, including these sort of run the movie backwards sort of things. And there's the theorists who work on these things say, yeah, electrons and protons should not look exactly the same in the mirror. They should look slightly different. So here's an electron. This is sort of my level of understanding an electron. It's got a negative charge. It's kind of like a tiny little ball. It spins, so it's got a magnetic moment. The magnetic moment of electrons are responsible for the magnetism in the bar magnets you stick on the refrigerator. Just inside that thing that you stick on the refrigerator is a bunch of electrons all lined up. That's where magnetism comes from. And for most purposes in chemistry, physics, engineering, that's about all you need to know, is that it spins, it's got this North Pole and South Pole. But there's a question, should this North Pole and South Pole be exactly the same? There's a school of thought in physics, the same sort of people who are trying to explain the origin of this Big Bang, this school of thought says they're not exactly the same. Well, the Earth has a North Pole and a South Pole, and they're very different. The South Pole's got mountains, the North Pole's got sea ice, North Pole's got polar bears, South Pole's got penguins. Yeah, okay, good. It's like sooner or later I was going to pitch right over one of those chairs for sure. The tension was getting too much for Dr. May. If ever you see a picture with, if ever you see a picture with polar bears and penguins in it at the same time, you're either at a zoo or you're looking at Photoshop, right? They don't exist in the same places. So the Earth pole, North Pole, and South Pole are very different. How about the electron? Well, the suggestion is that in addition to having a North Pole and a South Pole and a big negative charge, maybe there's a little extra positive charge near the North Pole, a little extra negative charge near the South Pole, or maybe the other way around. If that were to happen, this negative part near the South Pole adds up a little bit with this. This positive cancels a little of that, and it ends up looking as if the center of charge and the center of mass were ever so slightly offset from one another. This is the prediction, and this offset would be called an electric dipole moment, EDM, electric dipole moment, electron electric dipole moment. So this is the prediction. This is what people think could be a fossil of this original asymmetry. So people have gone looking for it, and what they were able to say as of about 2005 is, well, either that center of charge is exactly in the same place as the center of mass, or if it is offset, it's offset by less than this fantastically small number, 10 to the minus 27 centimeters. And you can compare that very small number with the classical radius of electron, which is 10 to the minus 13 centimeters. I take a ratio of 10 to the minus 13 and 10 to the minus 27, and what we're saying is, if this thing is out of round, if it's not a true ball bearing, if it's more egg-shaped than round, that's going to be less than 10 to the minus 14. So that's a fantastically round, symmetrical thing. And yet the theorists keep saying, yeah, well, that was a pretty good measurement. You got to do better because we're really sure this thing is asymmetric. So we set out to look for it. And we use molecular ions. And we do this experiment at NIST and at this institute called JILA, which is partly the University of Colorado. Over the years, I've worked for many years with this guy, Jun Yi, who is another NIST employee, in my opinion, the world's best laser spectroscopist. Here's a picture of him leaning over one of his lasers looking very dreamy. His graduate students tell me he hates that picture, so I always find a way of working it into my presentation. And we've had many students and grad students work on it over the years, and undergraduates, and we get funding from my beloved NIST and some from private foundation and also from the National Science Foundation. And here are some students, past and present, working on the project. So how do you measure something as tiny and very, very small as this possible outer roundness? There's a general rule in physics, which is if you want to measure something very carefully, convert whatever you want to measure into a time or into a frequency and measure that instead, because time and frequency are the things that we measure best in physics. This clock here is 300 years old, and it's actually was even back then, and even now, it's a remarkably precise object. Doesn't lose more than a second or so in a day. How does it work? Well, there's a pendulum in it, and the pendulum swings back and forth. So what can we learn from that? Why does the pendulum swing back and forth? Well, it swings up, and gravity tugs on it and pulls it back, and it swings the other way, and gravity tugs on it and pulls it back. And it's actually not such a bad way to measure gravity, or at least measure changes in gravity. If gravity were to be slightly different, it would swing, say it would get a little stronger, it would swing back and forth a little faster. If you were to take this clock, even a clock from the 18th century, and take it to the top of a mountain, gravity is a little weaker on the top of the mountain because you're further away from the center of the Earth. It would swing a little bit slower there, a rate you can measure even with this 300-year-old instrument. These days, physicists using, more modern clocks than this, using NIST clocks, can measure changes in clock frequency as small as 10 to the minus 15. This is way out of date. We're doing about a factor of 100 better now at NIST. Okay. So maybe we don't want to measure gravity. Maybe we want to measure how strong is this magnet. So this is supposed to be a compass, and you know that a compass is just a magnet on a little pivot, and it will pivot so that the South Pole will point towards the North Pole of the Earth, lets you find your way around in the woods. But if you wanted to use it to measure how strong this little magnet is, you could put the little magnet between a bigger magnet, and you could tilt it to the side, and if you tilt it to the side, the North Pole says, no, I want to point towards that South Pole. And it'll go a little too far, and it'll get pulled back and go a little too far, and it will wobble back and forth. And the frequency at which it wobbles back and forth, that's sensitive, that's proportional to how strong this magnet is. So if we measure it wobbling back and forth, we can make a very good measurement of that magnet. Or a much smaller magnet, like a proton. We're made up mostly of water. Water's got 2 hydrogen atoms. At the center of the hydrogen atom, there are protons. Those protons are also little magnets. You could take those little magnets and you could put them in a much bigger magnet. Oh, there's one right there. So what they're doing is they're taking this poor person who's full of water and therefore full of hydrogen and therefore full of protons, and they're putting his protons in the middle of this giant magnet, and all those protons are wiggling, and they're measuring the frequency with those protons wiggle. They give off radio waves, and by measuring as a function of position inside the body how fast they're wiggling, they can see tumors and organs and what have you inside the person. So basically, it's just that going on inside this MRI machine. There's the proton wiggling back and forth and sending out radio waves, and they collect them. But this is all about the magnetic moment. We want to talk about the electron's electric dipole moment. So instead of just having a North Pole and a South Pole, suppose there's a little positive and a negative. How would we see that? Well, we could take this electron and we could put it in a magnet, but the big magnet that we put it in could also have some electric stuff. We could put some positive charge up here and some negative charge down here. And the south pole will tug on the north pole of the magnet, but those positives will tug on the negative part, so the electric stuff will get into the action. And if there's an electric dipole moment, the electron will wiggle ever so slightly faster. And now we've converted this thing we want to measure, which is the possible dipole moment of the electron, into a frequency, which we can measure out to like 17 digits. So that's the trick. But if this is a very small electric dipole moment, if these electrons are only ever so slightly offset, we need to apply a very large electric field. And that sends us right away to two problems. First of all, if you take an electron and you put it in a big electric field, what will happen is you'll get sparks, or put anything in a big electric field. You take two metal plates and you put a charge across them. You can crank the field up to about 100,000 volts per centimeter, and you go any bigger than that and you just get sparks inside. Like, you shuffle your feet. Actually, there's so much humidity here in Maryland you don't even notice that. But in Colorado, where I live, you shuffle your feet across the carpet and touch the doorknob, and you'll get like a little spark sometimes. Okay, probably only on the driest possible days in Maryland, but in Colorado, it's an issue. That spark would happen anytime you try and make an electric field too big. So you can't get that big an electric field. And the other problem is, and this is I'm going to show you my PowerPoint mojo here. Okay, that took me like an hour. So we better watch it again. Yeah. You put an electron in an electric field and it just goes flying up, right? So you can't look at it very long. If you can't look at it very long, that's a problem. Because if you want to measure okay, so where in nature can we find a really strong electric field? Inside a molecule. I have to admit that I last studied chemistry in high school, which is a long time ago. I now work with molecules all the time. I had to learn a lot of chemistry, but I had to learn it on the fly. I picked it up from unsavory characters on the street corner, right? It's not, but I did finally learn some chemistry. But back when I was in high school, the way I thought molecules stuck together is you had like a positive sodium and a negative chlorine, and the positive stuck to the stuff. Chemists say that's true for some molecules, but that's not really how it works. I still believe this, though. The positive sticks to the negative. That's my picture of the molecule. In fact, when I think of molecules, I just think of their sort of nature's way of applying a really large electric field to my atom. This chlorine is negative. It's very close to the positive sodium. And in between it, there's an enormously large electric field. It's a much larger electric field than we could ever put in a laboratory. So if we could put our electron kind of in between the sodium and the chlorine, we'd have ourselves a high electric field laboratory built into a molecule. Okay, turns out sodium and chlorine is not so good because this has an even number of electrons and it's all paired up. My favorite molecule is hafnium fluoride plus. Hafnium is a very, very heavy molecule, and the fluorine is a very negative molecule. Sorry, hafnium is a very, very, very heavy atom. Fluorine is a very negative atom. Put them together, and I'm applying a large negative field to this hafnium, and there's some unpaired electron spin that lives in there. This is my laboratory for applying a big electric field to my electron. And then what else do we need? If we want to compare frequencies really well, what we need is a lot of time. So here are two grandfather clocks, and we want to go, which one is ticking faster? What we could do is we could wait for a minute, and we could count the number of ticks here and the number of ticks here, and they would each tick 60 times. Are the same? Or not the same? They're pretty much the same, but we could do better. We could count for an hour. This one would tick 3,600 times. This one also counts 3,600 times. They still see the same. Well, what if we count for a day? Oh, if we count for a day, this one is counting 86,000 and change, and this one is counting 86,000 and ever so slightly more change. After a day, we could say, yeah, at the rate of 1 tick per day, this one's going just a little bit faster. But to do that, we had to look at the thing for a long time, and that's characteristic of measuring really good frequencies, really good times. It takes time. So we need to watch them for a long time, and the way we do that is we put our molecules in an ion trap. This is a particular humane trap. We can catch and release. It doesn't really look like this. This is a trap for, I don't know, squirrels or something. Our trap looks like four metal tubes, which we charge up with electric charges in such a way that the electric field lines keep the ions trapped along a line down the middle of these things. So we have what's called an ion trap. It actually looks like this. It literally is coated in gold. It's quite sparkly. It's hard to see, but there's actually 6 rods here coming up covered with gold, and these end caps. The whole thing is assembled and put into a high vacuum chamber. And inside there, we can watch the electrons. Inside, we can keep the molecules in the trap. Inside the molecules, the electrons are doing that sort of tick, tick, tick I was talking about. This is the electron swinging back and forth. You can see it's the direction the electron is pointing is swinging up and down, just like the protons in the MRI machine, except about, several million times slower. Over the course of, this is milliseconds here, so over the course of a second, it's ticking only about 16 times. So it's ticking relatively slowly by atomic standards. But we can keep track of it going up and down, and we can measure that frequency super well. How do we make the electron tick, and how do we listen to it tick? I'm going to sweep a lot of stuff under the rug here. I've been working on this project for 15 years, and for 13 of those years, I had Junyi working with me, and it's pretty darn complicated. I will say that Junyi and I have made a lot of progress. Our chief competition is that, and it won't surprise you to learn that if the competition wanted to compete with NIST and the University of Colorado, they had to get a bunch of professors from Harvard and Yale together to compete. And if you don't mind, as someone from a fellow state school, when I mention the names Harvard and Yale, would you all mind going like, because they're the competition, right? This is, all right, thank you for that. So this all happens so mostly what we have is a lab full of lasers. Lasers are highly controlled light, and we use them for preparing and reading out the states, and so reading out the electrons. So most of the room is full of lasers. Way back in their corner, you can barely see it in this picture, is the little vacuum chamber where we keep the ion trap. Here's a notion to give you an idea. I won't walk you through this, but the molecules we use are unstable. You can't buy them from Alpha Chemical. We actually have to make them on a fly. We start with a chunk of metallic hafnium. We zap it with a laser. Some hafnium vapor evaporates off of that. We take sulfur hexafluoride. We flow the sulfur hexafluoride. Well, did I mention I didn't take a chemistry class? I'm having to learn all this. We flow the sulfur hexafluoride over the hafnium vapor. The hafnium steals the fluorine from the sulfur hexafluoride. Now it's neutral hafnium fluoride. The neutral hafnium fluoride molecules drift in a vacuum chamber into our electrode region, and we zap it with lasers and pop an electron off, and then we trap the ions. Whew. That's an oversimplification. Eventually, we dump the ions out, and we measure whether or not the electron is flipped over. So here's this ticking motion, and we measure that by, we measure these ticks up and down, and then you do a nonlinear fit. We try and see what sine wave of ticking fits this best, and we adjust the frequency of that sine wave until we find a sine wave whose frequency exactly matches that ticking. And then we do that. This takes about a second. We do that every second for about 2 weeks, and we take the average of all those frequencies, and that's the kind of measurements we do. Here's like conceptually, here's my hafnium fluoride molecule in the trap being lined up by we apply a relatively small electric field to line up the molecule, and then inside the molecule there's a much better electric field, and inside that molecule in that large electric field, the electron is ticking back and forth under the action of this magnetic field, and also hopefully under the action of this large electric field. And we do the experiment twice, once with the molecule lined up one way and once with the molecule lined up the other way. So we change the direction of the applied electric field, and we see if the frequency changes at all. And those tiny little difference of changes, we're looking for a change in the frequency much less than a millihertz, much less than 1,000th of a tick per second. Here's actually 2 years of data, and all these little points here represent one point, one measurement of the electron-electric dipole moment, and we average them all together. And if you look very carefully, you might say, well, geez, that looks like it's not averaging exactly to zero. Just even by eye, it looks like it's not averaging exactly to zero. That seems very exciting, but it's a lie. What we did is we asked the computer, which is analyzing the data, to lie to us. Now, why would we ask the computer to do that? It's because it's really, really easy in this art of precision metrology to fool yourself. We really want the electron to have an electric dipole moment. And every day we go in and we take data. And every day we get a slightly different number. The temptation is super strong, to say, oh, today it's measuring, we took a bunch of data and it measures slightly different from zero. And then yesterday we took a bunch of data and it measured right exactly at zero. Maybe there was a problem with yesterday's data. Yeah, come to think of it, I think there was a problem with it. Let's ignore yesterday's data. We're honest people, we're giving it our honest best shot, but we are humans and we've got our own desires. Scientists are people too. we want to save ourselves from this temptation. We are putting a lock on the freezer door. You know, however you want to think about it, we can't get at the ice cream. We told the computer, make a measurement. 2 years ago, we told the computer, think of a number, remember it. For God's sake, remember it. Now, add that number to every single measurement we make and tell us that. And then when we've finally looked at all the data, we decided we like the data, all the sort of supplementary measurements are saying, yeah, this data is good. We say, okay, now stop adding that number and tell us the answer. So that we're convinced, and whatever it tells us, we go with that number. And so now our own personal desires don't come into it so much. So we do this because, I won't walk you through this, but this is a history of precision measurement. Some of these measurements were made at NIST, I regret to say, where over the time, the sort of best, this is over like 30 years, the best measurements would sort of would drift around, but in sort of a correlated way, which kind of suggests that scientists were influenced by numbers they already knew. So we took all our data, we did statistics on it, we convinced ourselves that everything was, you know, the appropriate level of noise. And then what we did is we got everybody who was working on the project together into a conference room. We took a laptop with all the data, we projected it, and we said, like, okay, computer, right now, stop lying to us. It was one of the most intense moments of my professional career, because here's the thing. If it had been, like, distinctly non-zero, you know, it's back to Stockholm for me, baby, you know. But also, we're facing, what I forgot to tell is that there was this group at Harvard and Yale. Yeah, thank you. There was the group at Harvard and Yale, like, unfortunately, about a year or two before us, had also, like, for years, the measurement had a particular error bar, and they had done a measurement which was 10 times better a year or two before us, which we were a little sad about. And their measurement had very small error bars, 10 times smaller than the previous measurement, and it was also still consistent with zero. The error bars overlap with zero. We were about to do a measurement. We didn't know what our answer was yet, but we knew that our error bars were also very small, also about the same as Harvard and Yale, 10 times smaller. Yeah, good, this is very good. 10 times smaller. And so we had sort of like a double level of tension here. Like if we measured a number which wasn't zero, that would have been super exciting. But also, if we measured a number which was very distinctly different from zero, it would have been, well, it would have been very embarrassing for the Harvard and Yale people, right? Because they had already measured zero. So we didn't want to embarrass our colleagues. And so it turned out, there's the number. The electric dipole moment, 0.09 plus or minus 0.7 times 10 to the minus 28. So those error bars, plus or minus 0.7, added on to the 0.09, this overlaps with zero. In fact, it's almost coincidentally too good for zero. But basically, we had made a measurement with very, very small error bars, still equal to zero, still not answering this question, where does this fundamental imperfection come from? So there's, over the course of 40 years, 50 years, people have been working on this problem. The measurement has gotten 5 orders of magnitude better. There's the Brand X measurement. Here's our measurement. In the intervening years, okay, it had a lot of implications. About the same time as these measurements were coming out, the Large Hadron Collider in Switzerland was coming up empty. The predictions had been that they would have seen all these vast constellation, this vast zoo of new particles, that a lot of them would have addressed this question of the original imperfection, and they didn't. It was, you don't hear the particle physicists talk about it so much, but it was a huge disappointment for them. And part of it is that there was this thing called the minimal supersymmetric model, MSSM, which was everyone's favorite baby. They loved this model. It was mathematically beautiful. It explained everything. It solved all these problems. It had answers to the original imperfection, and it predicted all these particles. It also predicted an electric dipole moment, and it is now dead. And our group and the Harvard-Yale group were accessories to that murder, I confess. I feel good about it. Because, you know, facts are facts, theories are fine, but they have to confront, eventually they have to confront experiment, and that's a day of judgment. So we're still trying to explain that. In the intervening years, about a year ago, the Harvard-Yale group did a factor of 10 better. This must not stand. Not only do a factor of 10 better, but it's still consistent with zero. At this point, it's getting a little awkward because not only did it murder minimal supersymmetric supersymmetry, but it's murdering a lot of other theories too. We have a measurement coming up, which we'll release sometime either in this calendar year or next one, I don't know what the number is because the computer is lying to me about it, but we know that our error bars are getting smaller and smaller. So we can anticipate fairly confidently that soon we'll have a measurement here. And if I can draw that circle, why can't I draw a circle down there? Yeah, sure. But I think by about 6 or 7 years from now, we'll have another factor of 10. Got it all designed, just need to find some more money. If only Willie were still director, I'm sure he'd fund it. But maybe he can put in a word for me with his successor. All right, so that's kind of where we're at. This remains an open question. How can we answer this Psalm 51 measurement? How is it that we are born in this imperfection? It's really what we're working on these days. You can ask the question, okay, does it really matter to us what happened at this very early moment? Well, to me, it really does. I'll say that. Is that why we're funded? Probably not so much. Basically, what we're doing is an exercise in how carefully can you measure something. And careful measurement turns out to have a lot of applications to navigation, to communication, to nanotechnology. Probably the single most important, call it tech transfer product out of my lab is people. These days, the people that I train on this experiment are snapped up just as fast as I can train them mostly into the quantum computing industry, because these ion trapping, these laser techniques turn out to be just exactly what these people need. So, every week or two, I get a call. Hi, we have this new startup. Have you got any students for us? I go, get in line. So that's what we're about. I thank you very much for your attention, and I'm happy to answer any questions.
This is streaming. I still obviously reminisce for my days at NIST. So I'll run the clock back and I'll ask you the question I always ask employees. Why did you come to NIST? But more importantly, especially after the Nobel Prize, why did you stay?
Well, I came to NIST because really it was because of this. There was this institute where I could sort of be partly a university professor, partly a federal employee, felt like I could contribute to this national mission, but through this environment where there were young people around, it seemed like a great opportunity. Over the years, the reason I stayed turned out to be for my colleagues. There were so many good people who worked there. I will say that I had a lot of temptation.
Sure.
Some of these,
I know you did.
Some of these, both of these universities whose name we will not mention, so will come work for us. Yeah, thank you. And I said, no, thank you, because I was surrounded by people like June, people like Debbie Jin, people that I worked with all this, and you can't really find colleagues like that anywhere else. So that's why I stayed.
So I asked that question primarily for young people. I think you'll find, if you think about it, you really need to sometimes follow your heart. Because if you're doing something and working in an environment that really is for you, you never have a job a day in your life. It sort of becomes part of what you do while you're there. Obviously, this guy could have gone any place on this planet that he wanted to, but he stayed where he was. And obviously, over 45 years, I was tempted a few times to go also, but I didn't. And I didn't go because I believed in the mission of the organization. As I was making this transition from being totally selfish and sort of getting these 200 presentations to understanding that I could really contribute to this country in a way that I never thought about, by staying where I was and actually trying to facilitate the business of NIST, if you will. So get off my soapbox, and now we can open the floor for questions. If you'll stand up, give your name, rank, and serial number.
My name is Doug DeLuzin, and I'm a faculty here in the Department of Biology.
Mm-hmm.
Thank you for coming to speak. I really enjoyed it. And I guess I'd like a two-part question. One is, how long does it take to make the hafnium fluoride that you use in your experiments? And when you decided to use that molecule, was there already kind of a procedure to make that? Or did you have to get chemists to just like figure out how to make it for your experiment?
Okay, so the question is...
Being a non-chemist.
Yeah. So the question is, how long does it take to make the hafnium fluoride plus, and How do we pick that molecule? How do we learn how to make it? So I have to tell you, first of all, the making it is super fast. Well, learning how to make it took us quite a while. Now the process happens in about a millisecond. Like there's a flash of laser light, a little valve opens up and a puff of gas comes out, and about 1 millisecond later, the neutral molecules arrive. They're traveling about several hundred meters per second. They arrive in the trap. We hit them with a laser and bam. And that's all faster than you can wink, and so it's all sequenced by a series like the thing that triggers the laser, that opens the pulse valve, that flashes the laser, that turns on the ion trap. It's all in sort of a computer sequence. And we can do that about once a second. It takes about a millisecond, and then we spend about 1 second studying it. And in the process of reading out whether the electron is flipping up or down is a destructive process. That kills the molecules. We actually, contingent on whether the electron is up or down, there's a dissociation process. There's a sort of a higher level resonance. There's a dissociation process. We dump the ions out onto an ion detector, and they either go click or clack, depending on whether the electron was up or down. Learning what molecule to use was really tricky. I collaborated with a guy named John Bone, who's a professor at University of Colorado, husband of Debbie Jin, actually. He had a sort of a theoretical screen for going through a bunch of molecules. He had identified the symmetry. It turns out we want a triplet delta 1 state for this diatomic molecule. For me, it was a little bit of a shock because I come from a tradition of atomic spectroscopy, and if I want to do an experiment in an atom, and I need to know like what laser to buy to excite the atom, I go to tables compiled by former National Bureau of Standard NIST person Charlotte Moore, who like compile all, like basically any level transition you want in any of the 100 atoms. You can just look them up now. They're on the internet. It used to be in these big telephone book-like books. For diatomic molecules, you take 100 atoms times 100 other atoms. There's like 10,000. By the time you add up all the different ions, there's 30,000 different diatomic molecules. And I was shocked to realize that for like 95% of them, no one's ever written a paper. No one's ever done a calculation. And we ended up having to do, after John Bone predicted like this would be a molecule with really good properties, we had to do a lot of survey spectroscopy, really like 1950s stuff, where we're like sweeping, covering originally with gratings all the way up down to the finest laser stuff across, hundreds of nanometers of spectra, and then getting all the way down to the sort of kilohertz level stuff. So that took several years. As for making it, the original plan was to make a hydride, hafnium hydride, and the yields were very low. A chemist said, well, fluorine will stick to anything. So that was sort of our level of chemistry. And they said, moreover, fluorine will want to stick to hafnium more than it will to sulfur hexafluoride. So if you put those two together, you're just going to get some hafnium fluoride. Trust me. And he said, you'll have to adjust the levels, like the concentrations. Mostly it's neon. And it's seeded with about 1% sulfur hexafluoride. So we had to adjust how much sulfur hexafluoride, how hard we hit it, a bunch of stuff, and that was trial and error. But we would zap it with the laser, with a broadband laser, to ionize everything there, and we could analyze the charge to mass ratio. So it took us about a year to figure out how to do it. After we spent about a year fruitlessly looking for hafnium hydride, which we thought would be a better molecule. Turns out in the end it probably wasn't much different.
Dr. Spencer, and then Dr. Yu.
Thank you for breaking down such a theoretical, such a deep theory into some simple thing that we can even understand. I have two questions. One very simple, one needs some time. One is about your experiment all done at about 3 Kelvin. That's a yes and no answer. The second one is, could you break down about the quantum science, quantum computing to the audience here, where they are, where we're going?
Okay, so question was this experiment done at 3 Kelvin? And the answer is more or less. At the very beginning of this talk, I was talking about laser cooling and magnetic cooling in nano-Kelvin temperature. That's not this experiment. This experiment was done at a temperature of about 10 Kelvin. What we had is, we had neon under high pressure in a tank, and we just open the valve, and a little of the neon spritzes out. And you may know from chemistry that when a gas expands, it cools down. So at the same time as we were doing this chemistry, as the hafnium is sticking to the sulfur hexafluoride, it's in this little ball of neon that's expanding as it travels down the tube, and it cools to about 5 Kelvin, give or take. And then it comes into the trap, and we ionize it, and we use electric fields to stop it. And when it's all done, it's kind of wandering around in our trap. It's not exactly motionless. It's moving at, works out to about 20 meters per second, a lot slower than the gas. Gas here is like 300 meters per second, about 20 meters per second. It works out for this mass molecule to about 10 Kelvin, I guess I would say is the temperature. And it keeps that temperature until it has a chance to interact with the radiation from the walls. You know, the whole experiment is done in room temperature, which is at 300 Kelvin. Room temperature is 20 Celsius, whatever. It's about 300 Kelvin. And over time, it interacts, and the internal states of the molecule warm up, and as eventually the motional states of the molecule. So for the 1 second that it takes to do the experiment, it stays down around 10 Kelvin. You were also asking about quantum computing, and I have to tell you, that's really a multiple talks in itself. But it is a very, very hot field these days, and lots of companies, IBM, Google, Honeywell. There's a big Honeywell facility near Boulder, are working on this, as well as a bunch of those are the big companies and a bunch of little startups. The idea is that quantum mechanics allow things to be in superpositions, both 0 and 1. So, you know, if you have 10 bits, 10 zeros and 10 ones, classically that counts from 0 up to 1024 minus 1. Okay, so call it 1,000. 10 bits you have sort of represents 1,000 numbers. But if all those 10 bits could all be in superpositions of 0 and 1, it's kind of like at the same time they're all the numbers between 0 and 1024. You could sort of think of it as computing massively in parallel if you wanted to. That's not only is that an oversimplification, it's technically wrong, but it's probably going to be good enough for the answer to that question. But I think it was, yeah.
Thank you for the talk. I had a question more on your fossil experiment.
Yeah.
There are many people now talk about multiple universes.
Yes.
When you think about multiple universes, does that change your model of the fossils? And is it possible, is there a signature that could say, that you could look for that would say, yes, we do have the effects of multiple universes, or we don't?
So I answer the second question first. Is like, you know, the idea was about multiple universes. Is there a signature where we can answer the question whether there's multiple universes or not? The way it was explained to me, and this is already getting a little over my head, is there's not much of a signature. This question is, does it affect our thinking? And one of the reasons people invented this multiple universe question is to get at this thing. It's sometimes called the anthropic principle. Like, we live in it's almost like something out of Voltaire. Like, we live in the most perfect of all possible universes. The universe we live in is the universe which is optimized for people to live in. Whereas all those parameters that adjust particle physics could have been something very different. Where, say the protons and antiprotons were exactly the same and everything annihilated, there would have been nothing, light, no solar system, no Earth, no people. So in that sort of context of like there's lots of universes going on, and it stands to reason that we're in the universe which is adjusted for us to be in, that's a little easier to take in a multi-universe picture than in the idea that there's only one universe. Honestly, I find it all a little bit philosophical and not so much physics, because I don't think there's anything you can do to check on it. So I'm probably the wrong person to ask about it. I sort of feel like we're stuck with this universe. What can we learn about it? Although it does seem like there's this notion in particle physics which used to be very fashionable and it's now going out of fashion, called naturalness. Like, parameters should be 0 or 1. They shouldn't be like sort of fine-tuned to explain something. Like, if there's a fine-tuning where it's only the number has to be just exactly perfect for us to be here, there needs to be an underlying, more naturalistic explanation. That's going out of fashion, and partly it's because there is the idea that, well, we're here, so things had to be that way. I'm gonna stop now because I already said more than I know.
Okay, and we'll take maybe 2 more questions, and then I'll say that this afternoon, starting around 2 o'clock, Dr. Cornell will be here. We will make arrangements for any of you to come and chat with him at once. And my colleague, Keyshawn Moncrief, will give the logistics on that later. So Dr. Kamangar.
Well, thank you very much again, for a very lucid presentation that even enthusiast, understand. So you brought up 3 ideas to go back and look at the origins. One of them was looking through
Telescope,
which
yeah.
goes back to $13.4 billion, so we still have
Yeah,
quite a bit of a gap.
yeah,
The second idea was these colliders, and you said they turned out to be not as good as people thought.
yeah,
And the third one was just what you mentioned.
Yeah.
And the third one, as of now, you haven't found anything different from 0. Let's say we go 5, 6 years from now, and we do become either much more accurate and exact, we still turn out to be 0.
yeah.
Then what? Then what? Do we go back to, are there any viable ideas? Do we go back to scratch and think about it?
So, okay, the question is, we have the 3 ideas: telescopes, accelerators, fossils. What if they all don't work? Say it's 5 years, 10 years from now. So my own prejudice that I bring to this is that all this is sort of what I would call sort of various different ways of getting at particle physics. And I would say that over the last, in the 20th century, particle physics was an extremely glamorous area, and there was especially sort of the mid parts of the 20th century. The last 30 or 40 years, particle physics has been a little bit of a backwater in physics, and that's just the way of things. There's not written that some of the same problems that used to be the most exciting problems are going to continue to be most. I would say that in physics, if you're then going into career physics, rather than don't be like me, I would say a lot of the more exciting problems are sort of where physics overlaps with other disciplines, with biology, with earth sciences, with space sciences, with chemistry. And some of the most exciting areas in physics these days in science these days, are what we call the EV scale, sort of the biological chemistry sort of levels. And where physics can contribute to those, I would say has been where some of the most exciting stuff is physics happens. So I guess if that area of physics sort of, I don't know if I want to say wraps up, but sort of ramps down anyway, I don't see that as a huge loss. I think that's just sort of a natural, this thing happens. Every dog has its day, and maybe this area of physics, which I'm really interested in, is on the edge of wrapping up, and that's not such a bad thing. We might just have to be one of those mysteries that are left unsolved.
I'm Dr. Stojkovic of computer science, and my questions will be related to computer science. The first question is, how much do you use modeling, simulation, and visualization in your work? Because I'm sure they can faster your work and make cheaper. And the second question is it possible using the quantum computer or your experiment to make time negative, going little in the past?
So it was a computer science question. First part was, how much do we use sort of numerical modeling, computer science modeling, things like that in our experiment? The answer is enormously. We have, a lot of times we're very worried about systematic errors. And so we have elaborate numerical models. We do our own experiments, but we also compare our experiments to extremely elaborate quantum mechanical numerical models for the behavior of the ions in the trap. And we look for discrepancies to understand. First of all, we use these to try and predict weird things, try and explain weird things that we see. We look for discrepancies between our model. Part of our overall sort of quality assurance is a in parallel process of simulating everything, simulating the heck out of everything. Also, in originally figuring out which molecules to use, we did a lot of quantum chemistry, stuff like that. The other question is, can you get to negative time using our stuff? And I'll go out on a limb and say, yeah, probably not. But there was a question way in the back. I know that you were raising your hand for quite a while. Yeah.
Thank you for your talk, Mr. Ali. For the benefit of my students, Einstein said that not that he was smart, but it took time on the questions which were being answered. How long have you taken on some of the questions? Second, since you ended up with Psalm 51, verse 8 of Psalm 51 talks about, let the bones you have crushed rejoice. How many bones have you crushed?
Good one. Okay, in terms of time, well, on the Bose-Einstein condon experiment, I worked on that for 5 years with relatively little to show for it other than the enjoyment of doing the science. This EDM project I've now been working on since, I hate to say it, but since 2004, so that's 15 years. And I think the years don't quite catch it also because I think about this a lot, you know. I'm shampooing my hair and I'm thinking about it. You know, I'm going for a run and I'm thinking about it. You know, so it's an awful lot of thought has gone into, on my part and also of my students, my colleagues. So it's hard. It'd be hard to tally up how much effort has gone into these projects, and they're super. I've just barely. You might be able to catch. It's a very complicated experiment. There's a team of 10 super smart people working on it.
Okay.
And as for the Bones Crush, it's not for me to say.
I think I'm going to ask the president of the student body to come up. I think he had a few comments, announcements to make. But before he comes up, if he's still here, I had a question, Eric. How can you talk about the conflict, lack thereof, actually, between your pursuit of these fossils that lead back to creation and your faith? I think I know the answer, but I wanted to hear you share that with the audience.
I've never found, this is a sort of a personal subject, but I'll say that I have never found a conflict. It's just that way I've always approached these things.
Yeah. Okay. I guess I'll give you the sort of my answer to this, if you will. Actually, I have quoted Eric in some talks I've given at my church, as a matter of fact, and it's been that simply none of us are smart enough to define or determine how God went about doing his work. I guess the result is the beauty, the majesty, and the nature of the infiniteness of the universe. So basically, the universe is here. It's not for any of us to say how God created the heavens and the earth. And folks like Eric and other folks have been pursuing this for a number of years, trying to improve our understanding of the world that we live in. And there is nothing there that contradicts your faith. So.
That'd be my thing.
So, and after that, I'll ask Ms. Keyshawn Moncrief if she'll come up and tell us what we have in store for you and Dr. Cornell for the rest of the day.
Good morning, everyone. Thank you for coming out this morning. Thank you all for collaborating with us for the Grind Research. Just wanted to give you all an update on the schedule for those of you here for the Grind Conference. We're going to be doing lunch upstairs in Ballroom C. And then after that, if everybody's interested, we're going to be having student presentations for research that will be happening in room 212 upstairs. And then we'll also be having some interdisciplinary conversations with graduate students in room 210 after the poster presentation at 2 o'clock. So also afterwards, outside in the hallway, you will have the opportunity to meet with Dr. Cornell and also take pictures. So if you guys are interested in that, please join us outside in the lobby and enjoy the rest of your day and the rest of the conference.
Okay. I think that brings this inaugural symposium within the Business of Science series that we're starting. I dropped the ball, and I do not have our gift for our speaker, but I'll say in his presence, this gives me another chance to come out and visit your lab in Boulder. I will personally bring your plaque there. So thank you very much, Eric. So you're dismissed. And as it was heard, Dr. Cornell will be around for a while before he goes and gets his lunch to take pictures, speak with anyone who's interested. Thanks, Eric.
Thank you. I think that is my power thing, so I'm going to grab that.